Yeah, not ideal, but we ended up stripping apart all the parts of the one that's been underwater and putting them in a box to send back home to the UK after finding out that that chassis wasn't worth repairing. So now I've got to fix this tub and this engine, as the £145,000 that I've spent has gone to waste.
Matt Armstrong took a completely unremarkable, factory-restricted engine and turned it into a power monster that dyno operators said should not exist. The numbers it made broke every expectation anyone had for this platform. What he built and how he got there is the kind of story that makes engineers shake their heads in disbelief. The engine nobody expected. Matt Armstrong has built a reputation for taking ordinary engines and transforming them into machines nobody thought could ever exist.
Here is my RS6 engine. The engine decided to seize after I put the wrong octane fuel in it.
His latest project takes that reputation to another level. Starting with a completely unassuming engine, one limited by factory restrictions and designed around conservative performance goals, Matt pushed it far beyond its original purpose. The result is a build that produces power figures the engineers who created it likely never expected and may have tried to prevent. This project represents everything Matt has become known for. It begins with pure junkyard creativity, where forgotten parts and overlooked components become the foundation for something extraordinary. Pieces that most builders would ignore or discard are carefully reworked, modified, and combined into a setup capable of handling extreme conditions. Every stage of the build reflects a willingness to experiment and find solutions outside the usual rulebook. The fabrication process follows the same philosophy. Instead of relying only on traditional methods, Matt creates custom solutions designed around the specific challenges of the build. Standard limitations become obstacles to overcome rather than boundaries to respect. Every modification has one goal: unlocking the hidden potential buried inside an engine that was never meant to reach this level of performance. The final tuning process takes everything even further. Careful adjustments push the engine into a range where most factory guidelines no longer apply. Boost pressure, RPM limits, and power output are all taken far beyond what the original design intended. The finished result is an engine that seems impossible considering its humble beginnings. It was never built for this amount of stress, this much boost, or this kind of power. The original designers would probably be shocked to see how far it has been pushed. Yet the machine survives, delivering performance numbers that completely change expectations. This is the full story of how the build came together, from the weak starting point that should have failed to the hidden upgrades, extreme forced induction setup, advanced tuning, and final dyno results that stunned everyone watching. The weak engine Matt chose on purpose. The first decision in any build like this is choosing the donor engine, and Matt's choice here was deliberately contrarian. He picked an engine that, on paper, had almost nothing going for it as a foundation for extreme power. A high-mileage engine originally built with low compression, weak factory rods and pistons, restrictive cylinder heads, and a full suite of electronic safety systems designed specifically to prevent it from ever producing serious power. This was not a performance engine to begin with. It was a workhorse, built for reliability and emissions compliance rather than speed. The stock specifications reflected that mission completely. Low compression kept detonation risk down, but also kept power output modest. The factory rods and pistons were built to handle stock power levels with a comfortable safety margin, not to survive anything close to what Matt had in mind. The cylinder heads were restrictive by design, prioritizing smooth, quiet operation over maximum airflow. None of it was built with big power in mind. The real-world limitations went beyond the internal hardware. The engine had to meet emissions-compliant standards, which meant its entire design philosophy was built around control and restriction rather than output. It had built-in boost ceilings programmed into the factory electronics, designed to prevent the engine from ever seeing pressure levels that could threaten its survival. It had thermal weaknesses in its design, with cooling systems and material choices that worked fine for daily driving, but had no margin at all for the kind of sustained heat that high horsepower builds generate.
Originally I thought it gives you extra horsepower, but you do still have the 1000 horsepower all the time. The difference that key does is it puts it in top speed mode, which stops that rear wing.
Industry experts who looked at this particular engine before Matt got started were not optimistic. The consensus among people who understand engine building at a professional level was straightforward. The block would crack under serious boost. The cylinder heads would lift off the block under sustained pressure. The factory ECU would shut the whole thing down long before it ever got close to big power numbers, because that is exactly what it was programmed to do. These were not casual predictions made by people unfamiliar with the platform. They came from builders who had spent years working with similar engines and who had seen firsthand what happens when factory components get pushed past their intended limits. Their warnings were based on real experience with real failures, not pure speculation. That made Matt's decision to proceed even more notable because he was not ignoring vague concerns. He was ignoring specific, well-informed predictions from people who genuinely understood the risks involved. Matt picked this engine anyway, and he picked it specifically because it was one of the least likely candidates anyone could choose for extreme power. He took what was essentially a grocery-getter motor, built for nothing more exciting than commuting and errands, and set out to turn it into a fire-breathing drag weapon. Statistically, an engine like this should fail at roughly half the power target Matt had in mind. He ignored that statistic from day one and got to work anyway. Rebuilding the bottom end from scratch. If the engine was going to survive any kind of serious power increase, the bottom end needed a complete transformation. And this is where the real foundation of the build took shape. Matt replaced the factory pistons with forged units designed to handle dramatically higher cylinder pressures without deforming or failing. He paired them with custom connecting rods built specifically to survive the combination of high RPM and high boost that the final build would demand. He added girdle reinforcements and structural supports throughout the block to keep everything aligned and stable under conditions the factory design never anticipated. The oil system got a complete overhaul because an engine producing this kind of power generates heat and stress that a stock oiling system simply cannot keep up with. The crankshaft went through careful balancing to reduce harmonic vibration at the extreme RPM ranges this build would eventually reach. Matt applied special coatings designed to reduce friction and manage heat at critical wear points, extending the life of components that would otherwise wear out quickly under this kind of stress. Some of the most interesting work happened at the sleeve and block level, where Matt developed strengthening techniques on the fly that addressed specific weak points in this particular engine design. These were not solutions copied from a textbook or a forum post. They were figured out through direct experimentation, informed by Matt's years of experience and a willingness to try things that more conservative builders would consider too risky to attempt. The compression ratio went through extensive experimentation as well, with careful clearance adjustments made throughout the build process to find the right balance between making power and keeping detonation risk under control with the boost levels Matt had planned. What makes this section of the build particularly remarkable is the mix of parts Matt actually used. He combined budget aftermarket components with junkyard parts in configurations that professional engine builders looking at the build sheet called suicidal. The component choices on paper looked like a recipe for an early failure. And yet the bottom end that emerged from this process turned out stronger and more capable than many race engines that cost $20,000 or more to build from premium components. The harmonics and the oiling system Matt designed are specifically what keep this engine alive under conditions where basic physics suggests it should have already destroyed itself. This combination of cheap and unconventional parts working better than expensive, purpose-built race components is one of the more surprising lessons from this stage of the build. It suggests that careful assembly, smart clearances, and thoughtful attention to oiling and balance can matter more than simply spending money on premium parts. A budget rod installed correctly with the right clearances and the right supporting systems around it can outperform an expensive rod installed carelessly. Matt's approach throughout this section leaned heavily on that principle, prioritizing how the parts work together over how much any individual component cost. Opening up the heads, with the bottom end built to survive, the next major focus shifted to the cylinder heads and the entire breathing system of the engine. Because none of the bottom end strength matters if the engine cannot actually move enough air to make real power. Matt went through an extensive porting and polishing process on the cylinder heads, reshaping the internal passages to dramatically improve airflow compared to the factory design. He installed oversized valves to allow more air and fuel mixture into the cylinders with every cycle. He paired this with aggressive camshaft profiles designed to open those valves further and hold them open longer, maximizing the amount of air the engine could process at high RPM. Upgraded valve springs were necessary to control the valves properly under these much more aggressive cam profiles, preventing valve float and the engine damage that comes with it. Custom head gasket solutions and upgraded stud kits were necessary to keep everything sealed properly under the dramatically higher cylinder pressures this build would eventually produce. A standard head gasket and stock head bolts simply would not hold under these conditions, and Matt addressed that problem directly rather than hoping the factory parts would somehow be enough. The intake side of the build received its own dedicated fabrication work. Matt built a custom intake manifold designed specifically around the airflow characteristics of this particular build.
Means that, well, this is not salvageable. We're going to need a new block, and finding a new block is next to impossible. So effectively, we need a new engine.
And scaled up the throttle body to remove a bottleneck that would otherwise choke the engine's breathing at higher RPM. On the exhaust side, careful porting work and a custom header design maximized flow out of the engine, because an engine that can breathe in well but cannot exhaust efficiently ends up choking itself just as badly as one with restrictive intake. The results from flow bench testing told the real story here. The headwork on this build flows air at levels that have never been seen before on this particular engine platform. The volumetric efficiency the team achieved defies the engine's original design constraints entirely. This engine, in its modified form, breathes like a completely different piece of machinery than the one that rolled off the factory line. The forced induction setup. With a bottom end built to survive and heads built to breathe, the next phase of the build introduced the element that would generate the truly extreme power numbers, the forced induction system. Matt installed a massive single turbo setup paired with a custom fabricated manifold designed specifically to feed it efficiently from this particular engine layout. A massive intercooler was added to keep the compressed intake air at manageable temperatures, because heat is one of the primary enemies of safe high boost operation. The blow-off valve drama that came with dialing in this system became its own part of the build story, as the team worked through the pressure release characteristics needed to protect the turbo and the engine during rapid throttle changes. Getting the wastegate and boost control systems properly calibrated took real engineering creativity. The goal was instant spool, getting the turbo up to effective boost pressure as quickly as possible rather than suffering through the kind of laggy, delayed power delivery that plagues poorly designed turbo setups. Matt's approach to boost control wizardry on this build solved that problem directly. The fuel system needed a complete transformation to match the air the new turbo setup could provide. Matt installed a high-pressure fuel system including upgraded pumps, larger fuel lines, and bigger injectors capable of delivering far more fuel than the factory system was ever designed to handle. He added methanol and nitrous assist capability for additional safety margin and extra power on demand, giving the build extra tools to manage heat and detonation risk during the most extreme power pulls. The fuel itself shifted to E85, a higher octane alternative that provides much better protection against detonation at high boost levels compared to standard gasoline. Matt built in safety systems specifically designed for this kind of extreme duty cycle, recognizing that an engine pushed this hard needs more protection layers than a standard build would ever require. The boost pressures and turbo sizing Matt ultimately settled on are aggressive enough that on paper they should cause immediate compressor surge or outright engine failure. The plumbing and component sizing examined by conventional standards should have created either massive turbo lag or detonation problems severe enough to destroy the engine within minutes of serious operation. Instead, the system delivers lightning-fast spool and power that simply does not let up. Matt made this combination work through pure fabrication creativity, solving problems through hands-on experimentation rather than relying purely on textbook calculations that would have told him this setup should not function at all. The tuning that holds it all together. No engine build at this level of power can succeed without proper electronics and tuning work, and this build required a complete transformation of how the engine is controlled compared to its factory configuration. Matt converted the engine to a standalone ECU system, replacing the factory computer entirely with aftermarket engine management capable of controlling every aspect of the build's far more aggressive operating parameters. This required building a custom wiring harness from scratch, along with installing wideband oxygen sensors and a full data logging setup to monitor exactly what the engine was doing under every condition. Getting the factory immobilizer systems and various sensor conflicts sorted out took patience and careful troubleshooting, since modified engines running standalone management systems often run into compatibility issues with factory security and sensor systems that were never designed to work outside their original configuration. The actual tuning work involved careful knock control calibration, detailed timing maps adjusted across the entire RPM and load range, fuel curves dialed in to match the new injectors and fuel system, and boost-by-gear strategies that adjusted how much boost the turbo delivered depending on which gear the transmission was in. This kind of gear-specific boost control helps manage traction and component stress differently depending on driving conditions. The live tuning sessions involved real-time adjustments made while the engine was actually running, watching data streams and making careful changes based on what the numbers showed in the moment. This is some of the most demanding work in the entire build process, because mistakes made during live tuning can destroy an engine in seconds if boost or timing gets pushed too far in the wrong direction. The final tuning map this build ended up running pushes the engine into thermal and mechanical zones that every conventional safe tuning guideline would tell you to avoid entirely. And yet the result is clean, reliable power running on pump fuel availability through the E85 blend.
The E85 fuel is a blend of 85% alcohol and usually 15% petrol.
With the engine behaving predictably and consistently rather than suffering the erratic, dangerous behavior that aggressive tuning often produces when it is not done carefully. Reaching that level of stability did not happen on the first attempt. It came from repeated small adjustments, careful review of log data after every run, and a willingness to back off and reassess whenever something looked even slightly off. That patience during the tuning phase is easy to overlook compared to the more dramatic visuals of flames and boost gauges, but it is just as important to the final outcome. An engine capable of this much power is only valuable if it can also be trusted to run that way consistently, and the tuning work is where that trust gets earned. The dyno runs that broke expectations. After all the build work was complete, the engine went through multiple dyno sessions designed to progressively push power output upward while monitoring everything closely for signs of trouble. The team started with conservative baseline pulls, establishing a safe reference point for how the engine performed at lower boost and timing settings before working their way up toward the maximum output Matt believed the build was capable of handling. Each subsequent dyno session pushed the numbers higher, with careful attention paid to every reading along the way. The reactions from dyno operators watching these runs in person told their own story. Equipment strain became a real concern at the higher power levels this engine was producing, with the dyno cell itself approaching limits that operators do not typically have to think about. The ride, power figures, torque curves, and horsepower numbers that came off these runs broke records for this particular engine platform by a significant margin. At the most extreme power levels, the engine made numbers high enough that the dyno cell itself was at genuine risk, forcing the team to call multiple safety shutdowns during testing. This is not a normal part of dyno testing for most builds. It reflects just how far beyond typical expectations this engine had been pushed. And through all of it, the motor survived the repeated abuse of pull after pull and kept asking for more, rather than showing the kind of degradation or failure that most engines would display under this kind of sustained stress. At these power levels, most engines would already be scrap metal, destroyed by the combination of heat, pressure, and mechanical stress involved. Matt's creation simply kept making more power every time the team pushed it further, absorbing punishment that should have ended the build's life many runs earlier. What stood out most to everyone watching these sessions was the consistency of the runs. An engine pushed this far beyond its original design intent often shows signs of instability between pulls, with power numbers that swing unpredictably from one run to the next as components heat up and components shift slightly under stress. This build did not behave that way. Pull after pull produced numbers that climbed steadily and predictably, which told the team that the foundation work done earlier in the build, the bottom end, the headwork, the tuning, was holding together exactly as intended rather than masking hidden weaknesses that might show up later. Taking it to the street and the track, with the dyno testing complete and the power numbers confirmed, the engine went into the actual chassis for real-world testing, which presented an entirely different set of challenges than the controlled environment of the dyno cell. Getting the car ready for this kind of power output required serious attention to traction management, launch control calibration, and gearbox upgrades capable of handling the torque this engine was now capable of delivering. None of the supporting drivetrain components in a typical car are built to handle power increases of this magnitude, and addressing those weak points became its own significant project within the larger build. Street driving impressions revealed a car that, despite carrying this much power, remained surprisingly manageable in everyday conditions. Roll races against other serious performance cars and drag strip testing produced times that put this build firmly in territory most people would never expect from what started as an ordinary restricted factory engine. Heat soaking became a real concern during sustained real-world use, as repeated hard runs without the cooling benefit of a dyno cell's controlled airflow created challenges that needed solutions developed on the fly. Reliability issues that emerged during this testing phase got addressed directly, with fixes made between runs to keep the car operational through extended testing sessions. The end result is an engine that delivers acceleration capable of embarrassing supercars, all while living inside what is fundamentally a daily driver package. The car remains surprisingly streetable despite the radical nature of the build underneath it, while turning tires into smoke with every hard launch. This much power delivered through a lightweight car creates physics that modern traction control systems were simply never designed to manage gracefully, producing the kind of dramatic tire-shredding launches that make for unforgettable viewing. The contrast between this car's outward appearance and what it is actually capable of doing is part of what makes the entire project so compelling. From the outside, there is nothing that immediately signals just how much has changed underneath the hood. It looks for the most part like an ordinary car going about ordinary business. The moment the throttle goes down, that impression disappears completely, replaced by a level of acceleration that catches unsuspecting onlookers and competing drivers equally off guard. That gap between appearance and capability is exactly the kind of result that builds like this are meant to produce, and it is a large part of why this particular project has generated so much attention. Why this should not have worked. Stepping back from the individual stages of the build, the bigger picture here is worth examining directly. This engine, by every conventional engineering standard, was never supposed to reach anywhere near this level of power. The material limits of the factory components, the design philosophy behind the original engine, and the corporate restrictions baked into its electronics and emission systems were all specifically engineered to prevent exactly the kind of outcome Matt eventually achieved. Comparing the original OEM engineering approach to Matt's chaotic hands-on rule-breaking methodology highlights just how different these two philosophies actually are. OEM engineering prioritizes consistency, safety margins, emissions compliance, and long-term reliability across millions of identical units. Matt's approach prioritizes pushing past every assumption baked into that original design, solving problems through direct experimentation rather than following a conservative, pre-approved playbook. The lessons embedded in this build go beyond just one engine and one car. They are lessons about creativity, persistence, and a willingness to ignore limitations that most people treat as fixed and unchangeable. Matt Armstrong has proven, through this build and through his body of work more broadly, that the rules most people assume are hard. Physical limits are often closer to suggestions, conservative guidelines built around the lowest common denominator of components and methods, rather than absolute boundaries that cannot be pushed with the right combination of skill, creativity, and willingness to fail along the way. Looking ahead, Matt has more power on the table for future builds, along with new projects already taking shape and community challenges that continue to push him toward even more ambitious goals. This build is not an endpoint. It is another data point in an ongoing demonstration that factory limitations exist mostly on paper, and that real power comes from refusing to simply accept the boundaries that an engine's original design was built around. What makes this particular project resonate beyond the world of dedicated car enthusiasts is the broader principle it demonstrates. Every industry has its version of the factory engineer's warning label. Rules presented as fixed limits that, on closer inspection, turn out to be conservative estimates built around average skill, average tools, and an unwillingness to accept any risk at all. Matt's career has been built around testing those boundaries directly rather than taking them at face value. And this engine is simply the latest and most dramatic proof of how much room often exists between what is officially declared impossible and what determined, careful experimentation can actually achieve. It was never supposed to be this powerful. Matt built it anyway, and the result speaks for itself on every dyno sheet and every drag strip time slip this engine has produced so far. This engine should have failed at half this power according to every expert who looked at it before the build started. Instead, it survived repeated dyno abuse, dominated the street and the strip, and proved that factory limits are rarely the real limit. Matt Armstrong did it again. Watch the full build playlist for every detail behind this project. Subscribe and hit notifications because the next build is going to be even crazier.